On the 11th of March 2011, disaster struck Japan. A magnitude 9 earthquake devastated the northeastern side of Japan, unleashing billions of dollars in damage on the cities laying in this area. Subsequently, as the earthquake took place right next to the coast of Japan, a tsunami only added to the incredible destruction of the coast of Japan. It is estimated that 120,000 buildings were fully destroyed from the disaster, with another million buildings being partially destroyed. As one might expect from a disaster of this level, many hazardous and important buildings would most likely be affected. This is true with Japan that day, with the earthquake and subsequent tsunami striking the nuclear power plant located in the Fukushima prefecture of Japan. It was reported that despite the plant's resilience to the earthquake, a 15-meter tsunami struck and damaged the backup generators for the reactors, and the safety in place for the plant successfully shut down all three of the reactors in power. Despite this, the cooling system for the reactors failed, ultimately leading to the destabilization, explosion, and meltdown of the power plant. Three reactor cores had melted as a result. Radiation released due to the meltdown of the Fukushima nuclear plant was observed across Japan and the globe, creating a national emergency for the country of Japan. Unlike the similar incident which occurred at Chernobyl, Russia, the Japanese are comparatively proactive in the stabilization of the plant, taking measures prior to more problems showing up. Despite this, many problems in reducing the effects of the meltdown still occurred, and many human errors still took place in the analysis of the situation. This report will cover the attempts and problems of stabilizing the Fukushima power plant.
This is Hanaga Simbracha, so please introduce yourself and your work.
Hello everyone, hello James. My name is Hanaga Simabrata. I'm a geologist from Indonesia. Uh, I'm here as a master's student in Colorado School of Mines. So I have 5 years of experience in earth science, specifically petroleum geology.
Thank you. So, as you know, the project I'm working on is on the Fukushima nuclear disaster, which occurred in Japan 9 years ago. So, and as you probably know, the cause of the disaster was an earthquake that happened near the east coast of Japan. And can you just explain to me how that earthquake happened and maybe some of the factors that led up to it?
Okay, so you can basically generate earthquake in many ways. For example, during volcano eruption, you got earthquake, or in cases of meteor impact, which is very rare, that also generate earthquake. But usually, what we experience, the powerful one, those come from plate boundaries. So in the case of Fukushima, to the east, you have a you have a plate subducting underneath another plate on the island. So this is Japan Island. This is the eastern sea of Japan, right? There's a plate subducting underneath it, right? And as it moves down, it's kind of distort another plate here, right? So you build up potential energy, but at some point it's gonna fail, and that's how you generate earthquake.
And so, what you're telling me right now is that the the strength of the earthquake is directly proportional to the length of time between earthquakes.
That is exactly correct because the longer you wait, the more potential energy you build up, and then when it got released at the same time, it's gonna be like catastrophic. For example, like for the small earthquake, like 1 or 2 Richter scale, it happens like hundreds of thousands of times a year. But in the caliber of Fukushima, it's probably like decades or even century, because you need to build up a lot of energy first.
And can you quickly explain to me what the Richter scale is and what the magnitude 9 means?
Oh, okay. So Richter scale is a description of earthquake power. So from scale of 1 to 10, right, the power increases exponentially, right? So for example, Richter scale 1 and 2 is 10 times as much. So 2 is 10 times as much as 1. So 3 is 1,000 times as much as 1, right? Does it make sense? So 9 is like what? Like billion times as much as 1, right? So you get thousand, million, billion. Yeah, that's my second language, but anyway.
All right, and then going back to the original subject,
Okay.
how did the earthquake translate to the tsunami?
Okay, so go back to our little diagram here, when you build up energy, you are actually building up distortion of the crust, right? It deforms, right? So this deformation doesn't cause anything because it takes a lot of time. It's slowly, little by little. But when you have an earthquake, all of these displacement rebounds all at once. So imagine what happened to the water column. It's going to bounce up. It's going to create tsunami. And the stronger the earthquake is, the stronger the tsunami will be.
All right. Oh, that's very interesting. And
Yeah.
as we know, that the tsunami was the actual cause for this Fukushima nuclear disaster. So
Yeah, exactly.
thank you for that. And
Yeah.
then, lastly, as we saw, the Japanese appeared to be ill prepared for the earthquake. Why do you think that was?
They are actually not ill prepared. We just don't know better yet about earthquake. They're so unpredictable, and even if you can predict them, liability is kind of inevitable because they are powerful. Like you're gonna have building, destroyed. You can probably save life if you can predict them, but all those buildings are gonna, collapse unless in the future we find a technology that can withstand 9 point something Richter scale, right? So I don't believe they are ill prepared. This is just a bad day. That was just a bad day. Yeah.
Yeah, gotcha. All right, well, that's all the questions I have, though. Thank
Okay.
you for your time.
You're welcome. Anytime, man.
Okay, so here we are with one more thing. Han just wanted to clear a misconception before.
Yeah. So the power of a tsunami is proportional to the Richter scale. But on the other hand, it is also inversely proportional to the depth of the earthquake. And that is also true to what happened on the surface. So for example, you have 9 Richter scale earthquake, but if that occurs under like on the depth of 50 kilometers or 100 kilometers, it's not gonna be as deadly as when it happened like on the shallower part of the crust, like 10 kilometers. That being said, a smaller Richter scale earthquake can be deadlier, even deadlier than the bigger, higher number one if they're shallow.
And I think you were talking about like another scale that you guys use.
Oh, okay. So a very good scale that describe what actually happened on the surface is called the Mercalli scale. Scale from 1 to 9, it describes like it's descriptive, like what happened. Like for example, the scale 1, you wouldn't be able to feel it. It's descriptive, but Richter scale is more like energy. It's pure energy. It's measured in like joules or whatever.
All right, well,
Okay.
thank you for clearing that up.
Okay.
Almost immediately after the accident, employees from TEPCO, the Tokyo Electric Power Company, started analyzing the environmental effects of the meltdown. Concerns are put into place on the contamination of the ocean, ground, food, drinking water, and the damage to the plant itself. This allowed the Japanese to determine an appropriate course of action to stabilize the incident. The major issues at hand were the plant's inability to maintain proper cooling at the cores, which further damaged the plant, as well as the waste produced by the meltdown. Thousands of TEPCO employees, military personnel, and firefighters joined in the effort of shutting down the nuclear accident. An obvious concern post-meltdown was the radioactive releases into the air. The Japanese government ordered an evacuation 20 to 30 kilometers away from the site of the disaster to prevent health concerns involving radiation. Following the initial recovery efforts in stabilizing the area, which was only 4 days after the disaster, an explosion occurred due to the leaking and mixing of hydrogen gas with air, combined with the high temperatures of the plant. This explosion exacerbated the meltdown situation and the problem TEPCO employees would have to deal with. A significant issue with resolving the Fukushima nuclear meltdown, which was immediately recognized, was on-site exposure. Sending thousands of employees into a hazardous environment undisputedly came at a cost. as each of these employees risked poor health and potentially their lives by staying on the site for too long. Only up to 200 workers were allowed on the site each day, with each worker wearing personal monitors, breathing apparatuses, and protective clothing. Over time, TEPCO checked the radiation exposure of most of these people who worked on the site as a precaution in preventing severe radiation exposure. For reference, 1 MSV is the average radiation dose to an individual for 1 year in the United States. A dose above 250 MSV was the hazards level set by the NISA, which is the Nuclear and Industrial Safety Agency. Anywhere below this level was an allowable dose workers could receive in a short period of time at the Fukushima site. In the first year, many individuals working on the plant received concerning radiation doses, with 6 people receiving a dose higher than the 250 MSV level. In the years following, however, the radiation doses recorded in workers significantly dropped, a positive sign for their recovery effort. The main cause for the nuclear meltdown, and with a high number of other nuclear power plant disasters, such as the Chernobyl disaster, was the overheating or meltdown of the nuclear core. Thus, the high temperatures of the core was inversely correlated to the stabilization of the plant. In many cases, the overheating of the core causes a chain reaction of events, including explosions and leakages, which is exactly what happened with the Fukushima nuclear disaster. In order to manage these temperatures, Japanese scientists and engineers from TEPCO injected water into the reactor starting on the 14th of March, which is only shortly after the main incident. This would gradually reduce the decay heat of the reactors. A predicted consequence, similarly to the Chernobyl disaster when water was pumped to cool down the core, was a contamination of the water that was being pumped into the reactors, which could potentially leak into the environment and groundwater, furthering the hazardous effects on the environment. Temporary storage tanks were developed in order to store the contaminated water, as water was being pumped through the plant. Some of these containers developed leaks, which required fixing. Wastewater cleanup and processing systems were then implemented in order to properly clean and dispose of this contaminated water. These systems involved the filtration of contaminated water to remove radioactive material and reduce the danger of the water through several methods. In 2011, one of these systems was built using US and French technology, which is capable of processing 1,200 cubic meters of water per day. A more advanced and effective system was implemented in 2013 and refined in 2014. A concern rose pertaining to the filtration system's inability to remove all pollutants from the water, and its potential effect if the water is discharged in the ocean. The other option was vaporizing the water and releasing it into the atmosphere, which also had pollution concerns. In order to further prevent the leakage of contaminated water into the environment, the Japanese built many panels and shields around the nuclear site, which effectively shut down the flow of contaminants into groundwater in the ocean. Along with the problem of contaminated water, there was also a large concern for solid waste at the Fukushima plant. This included objects such as sludge, rubble, building materials, nuclear fuel, and radioactive particles. Most of these materials, if located in a hazardous area, were promptly removed and disposed of to prevent health problems. This removal of this hazardous debris minimizes radiation exposure and allows safer and further analysis of the site to eliminate all leaks and hazards. Much of this debris, including nuclear fuel, raws, and structural debris, still remains at Fukushima and is planned to be removed in the near future. As stated before, radiation released into the air or atmosphere was a major problem, as this form of radiation has the largest potential to spread across the environment and create hazardous conditions. Along with the ordered evacuation, workers built a cover over the reactors to reduce airborne pollutants released from the cores. Radiation levels were tested consistently across the Fukushima prefecture, with data released between 2011 and 2016 correlating with a significant reduction in radiation. Along with the physical measures taken to reduce the hazards and effects of the Fukushima nuclear disaster, the Japanese, along with the world as a whole, learned many lessons involving nuclear power plants and similar, dangerous, and large-scale projects. Many of these lessons include taking tangible precautions to reduce the likelihood of a disaster. This could include taking measures to prevent meltdowns or adding safety systems in the case of a loss of electrical power. Along with this, a large effort was made to improve the preparedness, communication, and mitigation strategies for employees working at nuclear power plants. The chairman for the NAIIC, which is the Nuclear Accident Independent Investigation Commission, fully admitted that, in quote, this is a disaster made in Japan. Its fundamental causes are to be found in the ingrained conventions of Japanese culture, our reflexive obedience, our reluctance to question authority, our devotion to sticking with the program, our groupism, and our insularity. End quote. This symbolizes that from an ethical view, due to the high risk of human suffering and death from the operation of a nuclear power plant, normal cultural standards should be rejected and replaced with a system emphasizing communication and safety. This exact situation was very similar to that of the Chernobyl nuclear disaster in Russia, in that human emotion, standards, and selfishness was partially responsible for the disaster in the first place. In Chernobyl, the rushed launch of the Chernobyl nuclear power plant, as a result of impatience and greed, caused the initial failure of the plant, as well as the complete disregard for safety precautions. Meanwhile, in the Fukushima nuclear disaster, although not having nearly as significant as an effect as in Chernobyl, Japanese standards, including poor communication, could have contributed to the initial disaster and arguably slow response to the disaster. Today, the Fukushima nuclear power plant has reached a much more stable state than from the original disaster. A significant amount of the radioactive waste has been removed, radioactive levels have been reduced around the area, and most potentially hazardous problems have been solved. Despite this, cleanup of the plant is still an ongoing process and will continue to be for the foreseeable future. Radioactive water, rubble, fuel, fuel rods, etc., are still present at the site and still need to be safely disposed of. Along with this, the safety of workers is also still a large concern, with the health of over 10,000 workers still needing to be maintained. The Fukushima nuclear meltdown is still a significant issue in the country of Japan and the world, and is a perfect example of the risks humanity poses to itself.